I just that doesn't treat it. Relative to me. Even though it's on that.
All right.
She's serious. Oh, yeah, that only works in Wisconsin. Yeah. Except I have the same thing though. I only have one that works in Wisconsin. Well, then what do you do? It's my parents. Yeah, that's not what I do. Oh, I did it well with my parents and I owe it to them. Yeah, but you want them to make our opinion, so. Yeah, I don't know, I just added that. Yeah.
Okay. Let's do a couple of quick recap. All right. Let's do a couple of recap questions. What is the solvent front? Yes,
It's when you put your it's when you put your sample in and then the solvent comes out first and it's like the giant, really tall peak, the first thing that you get.
Yeah, so it is a giant peak in GC, but it's a teeny tiny peak in HPLC. Sometimes you don't even see it unless you zoom in. It depends on the detector. Sometimes the solvent has, the detector has very good sensitivity to the solvent. Sometimes it doesn't. But it's really the moment of injection until all your void volume reaches the detector. The detector goes, oh, something hit me. And then you see that peak, a giant peak in GC, a tiny, tiny peak in HPLC. All right. So what is the difference when you hear retention volume versus retention time? And which one is more commonly used? Very good. You answered the second half of the question. Yes, retention time is the one most commonly used, but what is the retention volume? Yeah. Yes. So retention volume is the volume it took until a certain solute comes out. So but most commonly we use the retention time, the time it took from injection till you saw your component in the chromatograph. So what is the relationship of peak width and resolution? So if the width broadens or increases, what happens to the resolution, Emma? Exactly. So it's basically a wide peak is usually an indication of diffusion within the column and spreading within the column rather than going in and out and stay as a tight band that goes through the cons. So the lower the diffusion within longitudinally within the column, what did I say? I forgot. The more it diffuses, the wider is the peak. I forgot if I say the less it diffuses or the more it diffuses. The more it diffuses longitudinally within the column, the wider the peak, and that gives you less resolution because now there will be spreading of two components more, each will spread more, and if they separated well, then they won't separate when they spread too much. So if you had these two little peaks that separate nicely, but there's not a lot of time in between. So when you lose efficiency and when you lose properties of the column, then they might end up being like that. So this widen, and then you lose a clear separation. So you lose resolution. Very good questions, Emma.
For the solvent, that is the solvent of the actual right, like from the sample.
So yeah, but the solvent from the sample, and usually the solvent of your sample is similar to your mobile phase or immiscible with the mobile phase. Yeah. Very good. Any other questions before moving on? All right. So we want to talk about qualitative analysis and quantitative analysis. Now that you have achieved resolution or the needed resolution, then you want to do, you want to analyze your sample, your constituents. So you sometimes you just need to analyze qualitatively, meaning detect and identify. Sometimes you want to quantitate, which includes detection, identification, and quantification. So you might wonder, what's the difference between detection and identification? Do you know what I mean when I say detect, identify? Does it mean to you? Yes.
Like detecting is like seeing something's there, and
Yeah.
identifying is
What is it?
what is, yeah.
Yes, absolutely. So detecting meaning you saw a peak. There is a compound that is coming at a particular retention time, and you're seeing a response. Identifying is comparing it to a known compound or looking at the spectral analysis of it and comparing it to a library of compounds. So you're identifying, you're detecting, you're identifying. That's qualitative. So sometimes, depending on the analytical technique, if it's a mass spec, you get more information than just detecting and identifying. You get structural elucidation. Sometimes you get fragments with MS, you'll learn that next week, that allows you to piece the structural components together. Well, this is part of an aldehyde. This is just, it's an alcohol. This is a carboxyl group, this blah. So then when you piece it together, you identify. Okay, this is all qualitative. Quantitative is when you actually get a concentration. You will need a standard curve so that you can detect, identify, quantify. All right, so before we go into quantification, let's talk a little bit about qualitative analysis. So in order to detect and identify, you look at, well, first, is there a peak? Number one, yes. Then we look at retention time. And if you have a standard, then you look at the retention time of your standard and the retention time of your components, and you try to ID. You did that in both labs, in GC and a lab with the fatty acid methyl esters, and you did that with caffeine. You saw a peak, you compared it to the retention time of the standard, and you said, well, that's caffeine, most likely, or that's oleic acid or fatty acid methyl, what? Fatty acid methyl ester. Mouthful. For oleic acid, oleate or some methyl oleate. Okay, so that's great. Sometimes the peaks are too close from each other, and you're not sure, is it caffeine, is it some other phenolic or compound or alkaloid, then you're not sure really, you spike the sample, meaning you put caffeine, for example, in your sample and you see which peak increased. Because sometimes the difference, you have very good resolution and the difference is few seconds, 3-4 seconds. You can't tell if it is caffeine or another component that is coming too close to it. So you spike the sample. Another good way for identification is having a detector, such as a photodiode array detector. You all saw it now in the lab. So the photodiode array detector measures absorption and over a range of wavelengths, usually visible and ultraviolet. So over the entire spectrum of that, from 200 to 800 nanometer. Whereas a regular UV detector will just give you absorption at one wavelength. If you're lucky, you have a good detector, it gives you absorption at 2 wavelengths. Okay, so we will talk more about that in detail when we start spectroscopy section of this class, but your chromatogram, you have time here absorption units, let's say for caffeine, so you would see one peak if you have a standard and you just see the caffeine peak at, I don't know, 9 minutes, 10 minutes, I don't remember, somewhere around there. That is regular UV detection at 282, if I remember correctly, it's 282 nanometers. But with a photodiode detector, as all of you've seen already in the lab, you see the chromatogram at one wavelength that you select, which is, you talked about it, probably is lambda max. What is lambda max? Remember from lab? You don't remember from lab? Did you hear about lambda max? Okay. So it is the wavelength at which you get maximum absorption. So this is when you have the highest sensitivity. So usually when you're doing quantification, you really want to quantitate, get the area at lambda max. The wavelength at which you have the highest absorption. Okay, but also, Andres, I showed you another window, which is you're looking at a spectra. So you have here lambda for wavelength in nanometer over, absorption. So here, like every 0.01 seconds. So that's a three-dimensional wave. So every 0.01 seconds, you're getting a spectra. And you're seeing maximum absorption at 282 nanometer for caffeine. But you're also seeing that this caffeine can absorb at 235, it can absorb at 320, but it does not absorb at 400 or whatever. Just an example. So this is a fingerprint for your caffeine. It's a fingerprint. So photodiode array detector gives you kind of fingerprint, allows you to look at this and say, yeah, that seems to be a caffeine compound. Now, it's not always, what do you call it? It's not always unique to the compound itself, because some compounds have similar light absorption component. They will give you the same spectra, but they're not the same compound, but they have the same light absorbing compound in them. But it's definitely better for identification than just measuring absorbance at 1 lambda. Okay. We'll talk more about it in detail in the spectroscopy chapter, so don't worry too much. Sometimes if you do not have a photodiode array detector, you have a UV detector that allows you monitoring at 2 wavelengths. For example, it might allow you, for proteins, usually we measure at 220 or 218 to 222 and 280. So you can measure absorption at 2 different wavelengths and get the ratio and compare it to a standard. Then you can do better identification, because every compound absorbs differently at different wavelengths. So that gives you a stronger power of identification. Sometimes you have multiple detectors in sequence. So you might have a photodiode array detector, and then after it, you might have a mass spec. So you can detect under two different ways of detection, or let's say pulse amperometric detector, we'll learn about it later, and a UV detector. So they both look at different characteristics of the compounds. You might have multiple compounds going through. One can be detected because it absorbs light. The other does not absorb light, but can be detected by a pulse amperometric detector, for example. So having two detectors in a row increases your chances of identifying different components in your sample. Sometimes you need, like I mentioned last time, 2D chromatographic separation or 3D chromatographic separation, because one peak can be made up of multiple, because they have similar characteristics that allows them to interact similarly with the C18 column. But if we run them with size exclusion, they might have different molecular weight, so they can separate better. So you always enhance the separation by having multiple dimensional separation, then you enhance your detection capabilities. Detection and identification. A mass spec, you will learn about it in a few lectures. It gives you a lot of information. It gives you, well, it can give you the mass, the molecular weight, but also it can fragment a big compound into multiple fragments, and then you can piece that together and get structural identification. Okay. Any questions about qualitative detection for now? You will get more acquainted with all different types of detectors and mass spec in later lectures. All right, so now I want to spend a little bit of time talking about quantification. You did semi-quantification with GC, but you did actually full quantification with a KFE. But it all was based on getting peak areas. So when you get a chromatogram, you get a height. You can get a height. That means you can have a report that gives you the height of the peak, or you can get the area under the peak. We often go with area because resolution changes over time. So if your resolution changes, what's going to happen is this peak might just seem a little wider and shorter. Wider and shorter, you're still getting resolution, you're still able to identify. The area will be the same, equal, whether it is this height or this height. The area will be generally the same. The height might change, but the area will relatively stay the same. So we go with area when we want to quantitate. Of course, when you have two compounds present at very, very low concentration, the better resolution and the sharper the peak, the better sensitivity you have, because you're going to see a peak and it's traveling very, very tightly in a tight band down your column. The concentration is not spreading. You don't lose sensitivity because it stays concentrated and you get a really sharp peak. So you enhance the sensitivity of detection. So, but if it's present in good enough concentration, it doesn't matter. But in both cases, we look at the area. Only when it's presence in really small concentration, resolution is important. Sharpness of the peak is important because it enhances the detection. So it would be within the threshold of detection. The sharper, the taller the peak. Okay. So we used to, many moons away, decades away, we didn't have really advanced softwares. They would just have a strip chart recorder that would just help you determine the area under the curve. Or sometimes they would just take that whatever graph that comes from the strip chart recorder, cut the peak and weigh it. And that becomes used to be the way to do quantification, the weight rather than the area under the curve. But now, of course, we are living in luxury. We have very good data processing softwares that will just give you the area under the peak or the height or what you need for identification and quantification. All right, now I want to talk about external and internal standards. So I have a separate document, which I already posted for you guys on Canvas with illustrations. There's a question for your lab report. I think the GC lab report that talks about when do you need an internal standard? When do you need an external standard? If you need an internal standard, does it get added to all the samples in the standards, and why? Okay, so let's talk a little bit about that. Okay, so internal standard is a substance that you add at a known concentration and constant concentration in all of your samples and in all of your external standards if you're using an external standard. So what does it do? It corrects for sample preparation error. Especially for a method like has many steps, many pipetting, many reagents. You could lose some samples due to pipetting errors or transfer errors. So you want to make sure that you account for sample preparation error. Go ahead and you put an internal standard in your samples. So, but the internal standard should be very unique and not present in your sample, because you don't want it to coagulate, or if you are measuring fatty acids and if it is a C18, you already have C18. You have multiple C18. You have the saturated, monounsaturated, diunsaturated, and so on. So you don't want C18. You would want to pick something that is structurally similar to what you're analyzing, but not the same. Okay, but you don't want it to be very different that it will come out an hour later after all of your components come out. You want to make sure that it comes out within your analysis time. So that's the criteria: structurally similar, not present in your sample, and comes out within the same analysis time. So for example, C4, in your fatty acid methyl ester analysis, you don't have it in your sample. So that would be something that you would use. Okay. Now, what is an external standard? External standard is the same as the compounds you're analyzing. So oleic acid, methyl ester, the same as the one in your sample. Caffeine standard, same as your sample. So external means you don't add it to your sample. You prepare it separately from your sample and you use it to identify your components. And not only that, if you run a standard curve, like we did for caffeine, we can get an exact concentration of your caffeine in your sample. So external standards are needed for identification, for quantification with a standard curve. In GC, you used an external standard, but you did not prepare different concentration. You did not construct a standard curve, so that's why it was semi-quantitative. In caffeine, you actually prepared caffeine at different concentration, and you're plotting to get a standard curve that you can quantify. So external standard is not added to your sample, is measured separately and used to construct a standard curve, Internal standard is added to your sample, added to the external standard at the same concentration and meant to correct for sample preparation error. All right, let's give an example of using both. Okay, so let's say you have, okay, so the example here given is that you want to determine the amount of sucrose, glucose, and fructose in molasses sample. It doesn't have lactose naturally. Lactose is a sugar you find in dairy. So lactose can be the perfect internal standard. It has similar, it's structurally similar to the other sugars, monosaccharide, disaccharide. It's a disaccharide, and it will not coelute with any of them. So, and it will come out within the same analysis time. So it's a perfect internal standard for your sample analysis. So that's the lactose designated by the red drop. And then each of these sugars have a different color. Sucrose, yellow, glucose, green, fructose, blue. And then you are preparing different concentrations of the external standards because you're going in your samples, you want to identify sucrose, glucose, fructose, and quantitate. So you need external standards, different concentrations, so you can construct a standard curve. The lactose is your internal standard, and it's added at the same concentration in all of your external standard and the samples. Okay, then what? For every standard, you're going to have a lactose peak in every standard, and it has the same area because it's the same concentration. So in every standard, at every concentration, you're going to have a lactose peak. So what you're going to do is get the ratio of the area of glucose to lactose, fructose to lactose, and sucrose to lactose at every concentration. So this dot here, every dot is the ratio of one sugar to the standard or internal standard. And then you will have the known concentration of that glucose in concentration 1, concentration, oh, the green is glucose, concentration 1, concentration 2, concentration 3, etc. But it's the ratio, peak area of the external standard, glucose in this case, over the internal standard. And you do the same for sucrose and glucose. So the ratio of fructose area over lactose at each concentration of fructose. So now you have 3 standard curves. These are the ones that you would use. So you get the equation of the line y equal ax plus b for each standard. So you'll have 3 equations of the line. One for glucose, one for sucrose, and one for fructose. Then you analyze your sample. And you detect glucose, fructose, the internal standard lactose, and sucrose in your unknown sample. Then you take the area of glucose and use the glucose equation of the line. But you have to take the area of glucose relative to the area of lactose, and you use that as your y. Okay, so the ratio of your component of interest to the internal standard is your y. Then you calculate x, which is the unknown. And you do that for each one of them. Questions? Did I lose you anywhere? Happy to. We're good? Following? Okay. So just to recap, internal standard is added in all external standards and samples and used to correct for any sample preparation error. However, if you don't have an external standard, you cannot plot an external standard curve to quantitate. Okay, so external standards are still needed if you want to do quantification, so you can have a standard curve. All right. But internal standard, especially for analyses that had multiple steps, you need an internal standard to correct for losses during sample preparation. Okay. Questions before moving on? All right. High performance liquid chromatography is the last bit of chromatography I have for you before moving on to a different topic. And you're already pros now in high performance chromatography, thanks to Andressa, no? Yeah. Who wants to give the lecture? +5? 10? Come on.
Oh,
Do you wanna? Okay, come on. Try 2 slides. Let's see what you get. Let's shake it up a little bit. No.
Okay,
Love this. All right. Ladies and gentlemen, Emma and Al.
that's Miss.
Oh, Miss Emma.
Allie's actually the expert at HPLC, so she's gonna go first.
All right.
Alright, so we're gonna learn about HPLC, which stands for High Performance Liquid Chromatography.
Those are the vials of samples that the actual HPLC.
Those sample
Like-
beverages you analyze.
Yeah, so the needle like goes into the top of it.
Yeah, there are actually samples from a few years back. One of my TAs was creative and did that for us. I want to say one more thing. It used to be called high pressure liquid chromatography. Because you would pack it under pressure and it gives you a really high back pressure. But then they improved that over the time. That's why it now no longer called pressure, it's called performance. That's the.
So HPLC versus traditional low pressure liquid chromatography. What do you guys think? Do you think it has do you think HPLC has better speed or traditional low pressure chromatography?
Come on, interact with your teachers.
HPLC.
Why?
High performance.
Yes.
High performance.
Yes.
We just said it, it was high pressure. So high pressure is better for speed because it can push the solutes, push your solutes faster through the column, so you can get better analysis.
HPLC also has better resolution than traditional low pressure liquid chromatography. I'm getting a little anxious.
Yeah, why? Why does it have that resolution? You just kind of answered it in the previous one. It's packed more efficiently, so you don't have a lot of volume between the particles. So the particles are fine ground, well packed under pressure, so there's not a lot of space between the particles. So there is no high mass transfer. So that means the components are not really lost going in and escaping. And they travel tightly down your column. Very good. Do you have visible columns?
These are these are both HPLC columns.
Mhm.
These are what go in the oven. They're expensive and they break. And I think these are probably broken or
Well, excessively used.
these are well used. But they're different from like gas chromatography specifically because like they're thicker and
Has anybody taken the OCHEM lab? When I think the low pressure chromatography, you're talking about the column chromatography. So you have to manually pack that, which obviously causes for error, which is why there's higher resolution. And then you can't reuse it because it can't you can't rinse it with another thing because you have to throw it away already. So that's why this one is also better for the environment.
Yeah, that is correct, but I wanna say reusable columns that you don't need to pack, unpack. But, and there's a packs and packs for other column a lot to clean it, so you can run multiple injections on like a low pressure packed column. But at some point, you have to empty the column, wash the media, and repack again, because also sometimes you have gaps. That's very lost, and you have gaps or cracks that you have to refill the column over again. So the reusable column here means that you don't unpack and pack. It comes packed, ready to go, and usually at least 1,000 injections.
And then you can recover your samples from HPLC pretty easily. And like HPLC usually only uses like 2 microliters per run. So you can then do further analysis with the same vial of samples.
And you won't necessarily lose any sample if you, because the machine will do it for you. They'll recover it for you. So it's not any manual recovery. So you won't lose any. And the machine also does analysis for you. Because I'm just thinking column chromatography right now for the other.
Low pressure can connect to a detector as well,
Mm.
and high end detector that can do the detection and analysis for you. Yeah, what I want to say is you can inject as low as 1 microliter, even if you have ultra pressure or ultra performance with very small columns, but you can inject up to 100 microliters or a little bit more. Well, that column, the big thick one,
Mm-hmm.
so it has better capacity, more capacity.
This is the one you use.
It's big. So these are the components of HPLC.
You're doing great.
There's a computer that shows your data collections, and the column. Yeah.
Talk about them in order.
Okay, so
First.
What's in
yeah.
the reservoir?
The reservoir is where you put your samples, right? Or
Well, you have an injector for the sample, right? But what's in the reservoir? Is what's moving through your system.
The eluents.
Yeah, the mobile phase, right?
Mhm.
Yeah, okay.
So the reservoir holds those?
Yeah, the reservoir holds your mobile phase, and then what makes the mobile phase go through your column?
The pump?
The pump.
Yes.
And then the injector is what? Where you put what?
The sample.
The sample. And then the sample goes onto what?
the column.
Mm-hmm.
And then your mobile phase does what?
It pushes the columns based on
Yeah,
polarity.
pushes the
and-
sample
yeah.
from the pump
Mm-hmm.
and takes it where?
To the detector.
To the detector. And the computer does what?
It gives you the,
Chromatograms.
yeah,
The data.
yes.
Perfect. All right. Let's do each 5. Not 10. 10 together. 10 together. 5 plus 5 equal 10. Good job. I love the courage. All right. Be prepared. Each one of you can do that in the following lecture and get points. All right. So you all seen the components of HPLC. Sometimes you have more than one pump. So in the lab, you had a system where you had 2 pumps, 2 reservoirs, and each was pumped through one pump. We had pump A for reservoir A and pump B for reservoir B. Then we had a mixer that mixed a different proportion because you were doing isocratic or gradient erosion. Gradient, you had 2 mobile phases and you were building a gradient. So each pump was pumping a mobile phase, mixing them under high pressure, at least the example in the lab, and then go through the injector unit where you inject your sample and the mobile phase carries the sample onto your column. And then these different components start interacting differently with the stationary phase in the column, causing them to separate from each other. And each separated component, hopefully they're well separated, well resoluted, will get to your detector. And we'll talk about the different types of detectors. In the lab, we had a UV detector, specifically photodiode array detector, that gives you data or information that gets converted to a chromatogram. So, and then you read that, you get reports, very easy, convert the areas to concentration using standard curve. Sometimes after the detector, you have a fraction collector. And that's what Emma meant. You can, or I don't know if it's Ali, you can collect the sample rather than going to the waste. And sometimes we do multiple injections to collect enough volume that we can take and do further analysis, like take it to the mass spec and do structural elucidation on the samples that we have collected. I want to say that with low pressure chromatography, you can also collect the sample, but because you don't have very good resolution, if you really want pure sample, you really need high performance liquid chromatography. But if you are not really collecting different fractions that you really want them to be pure, you can use low pressure liquid chromatography in a preparatory form and still collect fractions. You can collect fractions, that is, from the two different types of chromatography. Okay, pumps. You've seen the pumps in the lab. You can program the pump to pump at a particular rate. And the pressure changes based on the components of the mobile phase. Usually water has causes higher pressure than acetonitrile. But you don't want the pressure to exceed the maximum allowable by the unit. Otherwise, the media within the column will break or disintegrate. So we want to make sure that the pressure does not exceed a maximum allowable by the manufacturer of the column. Okay, so, but we set it at a certain rate, and the rate impacts resolution like we talked about last time. So in lab, you set it at 1 mil per minute. And that gives us good resolution for the purposes of our analysis. Sometimes it can range between 0.5 ml to 1.5 ml rate, depending on the purpose and the analytes. And then in lab, you saw a high pressure mixing unit. So we had two pumps, and each pump is pumping a mobile phase under high pressure, and then they go into a mixing chamber and they get mixed under pressure. This kind of system gives you very consistent mobile phase and very low noise in your chromatogram, because your mobile phase is mixed, especially for gradient elution. You want them to be mixed really, really well under pressure, so you have a very nice baseline. Some systems have one pump and like 4 different mobile phases. So these can get mixed under low pressure before entering the pump, and then the pump pumps them into the injector. Still get good mixing, but probably not as efficient as high pressure mixing. Then the injector, you saw in lab, the auto injector, where the needle itself wanders and goes to the tube based on the program, the number of the tube, and goes into the septum, which is the cover you had in that rubber area. It penetrates that rubber, goes in and takes out a selected volume that you have programmed it to. In the case of what we had did in the lab, it was 20 microliters. So the sample loop, you probably saw that as well, right? There are different types or volumes of sample loop. It can be as small as 10 microliter sample loop, or it can be as big as 200 microliter sample loop. So what happens is when you inject the sample, there are internal valves that open, allowing the mobile phase to go into the sample loop, carries your sample, and takes it into the stream of the mobile phase onto the column. And then it closes again. The valves close again so that the mobile phase pipe bypasses it. Doesn't always have to go through the sample loop, only when it's carrying the sample at injection. And then you did see the manual injector. Why, I don't know if Andressa asked that question. Why would you need a manual injector when you can potentially have an auto injector? Budget, it did go over. Yeah. So in the lab, we have two, if you've seen them, the manual injector and the auto injector. And who uses the manual injector in our lab? Did Andressa tell you? You didn't tell them? The least favorite student. No. Usually, if we have many students needing the HPLC and we only have a few of them and budget, so we have the manual injector. So usually the student that have very many samples, like 50 samples to run, will get the auto injector, and the student that have 5 samples to run will have to be sacrificed and using the manual injector. So it really depends case by case, but yeah, it does help to have multiple units in the lab, especially if there's a big group trying to do research. The benefit also of an auto injector, you can buy a unit that store them in cool conditions. I'm losing my words. I don't know why today. All right. So it's a refrigerator kind of coolant so that if you have components that degrade over time, you have 50 sample, each run is 30 minutes, and you worry about potential degradation of the components overnight if you're running all of them overnight. So you want to keep them cool to prevent degradation. So that would be nice. You would get a cooler and you put it at 4 degrees and you run your samples overnight and not worry about them getting degraded. Okay. So columns, like Emma told you, we have different types of columns. You have different dimensions of columns, and also you have different lengths of columns. So the longer the column, if you have a lot of components, the better the resolution, because you have many theoretical plates that allows good separation. So the longer the column, the narrower the column, and the longer the column, the better the resolution. Narrower also means you reduce the mass transfer factor. So there's not a lot of time spent on the stationary phase. It goes in and out faster. So the thinner the column, the longer the column, the better the resolution. However, sometimes you want to use a bigger column to have better capacity. So it depends on the purpose of your experiment. If you really want to collect a fraction and do further analysis, you want to inject 200 microliters instead of 10 microliters or 20 microliters. So you get a thicker column. So you lose a little bit on resolution, but you can inject more. You gain on capacity. So if you remember, Gary showed you the triangle of resolution, capacity, sensitivity, all of that. What do you want? It depends on the purpose of your analysis. All right, and then there's also a very thin column, or even like this kind of column, short and thin as well. So, and I don't have a UPLC column. It can be even smaller and thinner. So many different options. And as Emma told you, you don't want to drop it because the internal stationary phase can break inside and there's no way you can fix it. Once it's dropped, it's goodbye, back bad news to your advisor because they will have to buy you a new column. And also you cannot cut a column like you do in GC, right? In GC, you cut the top of the column because you want to remove all the impurities that, just got deposited on that column. But you cannot do that with HPLC. What do you do instead of cutting the column? Because you can't cut the column. And then you have impurities that you don't want to contaminate the rest of your column. Guard column. There you go. So we have little components, guard columns and fitting tubing where the guard column can go inside. And it goes between the pump and the column. So anything coming in your sample that is impurity, let's say you have a C18 column, you have impurities that can bind very strongly to your C18 column and blocks, reduces the capacity. You don't want that to happen and you lose the life of the column. So you use a guard column, a pre-column, guard column that captures the impurity, and then you change the guard column more often. So usually every 3 months or 300 injections, you throw away the guard column or cartridge, whatever you have, and then you put a new one. And this way you protect the life of the column longer. Because if impurities land on your column, oh no, but you're sitting quietly over time. All right, so if impurities land on your column, then you don't have functional groups are blocked, you lose resolution. All right, you guys, thank you for being so nice. And thank you, ladies, for giving us intro. Good job. Yes, it's all right, sounds good. I'll see you on Friday.
When I had the bread,